Well, hello, you guys. My name is Onur, and I will be going over a StarCM Plus tutorial on transonic flow over an airfoil using an overset mesh. And the first question that may pop in your mind is, what is overset mesh? Where and why is it used? So I will go over those definitions, and then we will proceed with the simulation tutorial. Okay, so the first question is, what is an overset mesh? It is also known as overlapping meshes, and it consists of a domain which has several generated meshes throughout. So there must be two or more meshes generated inside the domain. And what is the main use of the overset mesh? It is generally used to model large motions accurately, such as the linear velocity of a car, or I mean, a car traveling at 100 kilometers per hour on a road, let's say, or a plane traveling at 700 kilometers per hour in the air, stuff like that. And it also allows us to do parametric studies in which several cases of flow must be analyzed, such as in our case in this simulation that we will analyze. It will be analyzing the various angle of attacks of an aircraft wing against an airflow. And also in terms of practicality, it saves a lot of computational time, meaning that you don't have to generate the same mesh over and over again every time there's a change of the position in the domain. Change of the position of the parts in which is the airfoil in our case. And so this saves us a lot of time. Okay, so generally an overset mesh requires a background region which encloses the whole region, the whole part, and an overset mesh which encapsulates the part. Encapsulates meaning it surrounds the part. So the background mesh in other terms will be your actual domain, and then inside it there will be the overset mesh or meshes. And in some cases, these are special cases, there might be no background meshes to work with, such as there maybe for gear pumps, but there will, well, yeah, let's say gear pumps. Like there will be two gears turning, and they may not require a background mesh, only each other. So that's a special case, and which will not be covered in this tutorial, but it's good to know. All right. So here in figure 2, you can see the whole domain for our tutorial. The red region, which you can see on the right here, will be our the overset mesh, and the gray region will be our background mesh. All right, and you can see the finer mesh around in the background region, and this will be the this will where the airfoil will be. All right. So how does it work? It works with a hole cutting algorithm, and in figure 3 you can somewhat see uh, you can see how it works, and I will explain it better now. In a sense, the overset mesh cuts a hole in the background mesh, and by this cutting, it can project the part inside the overset mesh on the background domain, the background region, let's say. So there are two regions, the overset region and the background region. So the overset mesh will project its part to the background region. All right, so once it does that, once the interface is initialized, there will be three types of cells, which are active cells, where the governing equations are solved, such as Navier-Stokes equations and energy and all that. And there will be inactive cells, where the equations are not solved. And the third type would be the acceptor cells, which are cells that will separate active and inactive cells. And they allow the information transfer between the background and overset regions, let's say. And for every acceptor cell, there must be a matching donor cell surrounding it for information interpolation. So if you come back to figure 3, you can see in red the overset cell, the acceptor cell, and behind it the um, the black cells would be the donor cells. So between these, the acceptor cell and the donor cells, there's an interpolation going on. So in this case, it is the inverse distance interpolation. So what the interpolation does is that it gets information from this top, let's say the top cell here, left cell, the right cell, the bottom cell, the one in the middle, and interpolates all those informations to one point, which is the acceptor cell here. And through that interpolation, the information transfer just occurs throughout the whole domain. Okay. So okay, again, in figure, this should be 4, I'm sorry. In figure, anyways, let's proceed with figure 3. You can see the whole region, which consists of the background and overset regions, combined. So yeah, the active, inactive, and acceptor cells you can see in blue. And acceptors are in blue, active are in green, and inactive are in red. So if you would like to see the only background mesh background region, sorry, we can see the inactive cells here, and then the acceptor cells in blue. But where you can, so wherever there is an inactive cell in the background region, there will be a corresponding active cell in the overset region, and depending on the regions, there will be the acceptor cells. So you can see the difference. Alright, so we can now, I explained most of the basic stuff, and we can now proceed with the simulation in StarCCM. Okay, first you open your StarCCM, and before I begin, there are different versions of StarCCM. So for example, my version is 15.06.2020 version, but you may have something else. So the stuff I might have here, you won't have them. Not like major things, but some minor things you won't be able to see. That's not important. They're generally under in some other different settings. They change these settings sometimes, so don't panic. It's mostly because of the differences between the versions. Okay, so that's out of the way. Let's proceed with our simulation. We begin by opening a new simulation file or creating a file here. Or you can just go here and say new. They're the same. And you'll see a window here which will ask you to choose process options and some other options here which I will come. The process options meaning that your CPU, which has like multiple cores in it, will either run in serial or in parallel with each other. I generally choose parallel because the information is processed in parallel with each other, so they share the information to process. If you have i7, you will generally have 6 cores. I have i7, I have 6 cores, but you won't really need more than 2. I'll just say 4. And the next step is the license. You don't have to touch these. And the license, you obviously need a key, and you have to activate the power on demand boxes over here, these two. And then you insert your key, of course, like I said, and then you say OK, and your simulation will begin. Okay. So your window should look something similar to this. Sometimes you won't be able to see the properties window in here, and if you don't see it, you can always toggle it from this window tab over here, say properties, and it will show. This is important since once you click on something, it should show you this properties and just allows you to work with these. Well, first, what we have to do is we have to generate our own CAD, and that is implemented in StarCCM. So you open Geometry tab, you right click 3D CAD models and say new. And here you'll see a window like this. So first we need an airfoil, and we can't really draw it by hand, take time. So what we need to do is find an app that will automatically give you the airfoil you would like. And we can do that by using the Java foil app here. You don't have to download this. You can actually use the web page, but it wasn't working for me. So what I did was I just simply downloaded this app, and you can use it with ease. And we will provide you the link for it. So okay, this automatically creates your airfoil. I previously put my desired values here for thickness, for camber, and camber locations. Let's go with 4, the first option here. The thickness should be 13.5, or you can choose something else, doesn't really matter. Camber is 2, camber location is 1. Oh, sorry, this is not 1, this should be 24. That changed, so yeah. And this wing foil, airfoil is actually the airfoil used in World War II aircraft called Spitfire. So it's pretty cool. And the next step would be to save this, update your view just in case. And save this to desktop anywhere you would like. Say it as NACA 2213, I think it was there. 13 Airfoil. Okay, save it. Now the next step would be what this does. Like, you're pretty much saving the coordinates of the points here. You can see them here. You close this window. Next, you have to open a Excel file, and then you have to open in the desktop this one over here. So I had previously done these, so ignore these for now. So we have our points in this file. Click on it, say OK, say next. You don't have to change anything else here. Now all you have to do is delete this, otherwise delete the title there, otherwise it won't accept. Put those there. And then, so what this represents is the A column would be the X coordinate, B would be Y, and then we need a Z in order for star CCM to accept the file. So we put 0 here and extend this line column downwards. Again, we have to save this as CSV file. So desktop again. Yeah, CS, this one. Yeah, sorry. CSV comma delimited. Alright. And we can just put this, say save, say OK, close this, and then go back to start CM. You right click here, the 3D CAD model 1, say import 2D curves. So the previous one I have done is here. The one I have done right now is this one. Say open, say OK, and here's your airfoil. So the next step will be to save our simulation, and you can save it anywhere you would like. Let's name this Overset Airfoil tutorial. Let's save, and it should be saved. Now, before we extrude this, there's a problem with the sketch, which is that if you zoom in at the trailing edge of the winglet or the airfoil, you would see that the sketch is not closed. So this prevents us from extruding the sketch. And in order to fix that, we have to right click and say edit to the sketch. And in the sketch, choose the line option, pick a place for it. Also for the bottom part, do that. And then the next step would be applying a constraint, apply a tangent constraint by holding Ctrl, selecting this line and the line created by the airfoil. And then right click and say apply tangent constraint. Do the same thing for this one as well. Well, you can kind of change it. Okay, let's do it again. For this part, let's do it like that. And then choose them to hit that. Okay. So in order to cut the protruding parts, you choose the snipping tool here, trimming tool, and then we cut these parts. So it automatically just creates a conjunction here, which encloses the sketch. Hit OK here for the trim. Hit OK here, and now we can actually extrude our airfoil. And what is important here is that your extrusion option should be one way, because later on we will convert the meshes, 3D meshes to 2D, and whatever we create here should be extruded to one side and should not cross the Z, -Z axis. So just keep everything the same except for body interaction. So merging means that if there are other bodies in this part, they will merge. So we don't want that. Say none and hit OK. So here's our extruded airfoil. Now, if your view gets messed up, you can easily fix it by looking at this axis here. And you can see that once we orient your airfoil this way, you can see that positive Z axis is looking towards you. So basing that, you go to the camera symbol here, click on it, say views, and then you come to positive Z because Z axis is looking at you, and say up Y. So here we go. We can actually store this view for ease, and then once you, let's say you messed up again, you can say restore view and say view 1, and it automatically restores your view. Okay, so the next step would be actually creating the overset region for this. So for that, you choose XY axis, XY plane, say right click in, I say create sketch. And what we will do is that we will, for 2 meters from the tip of the airfoil, we will extend for 2 meters, and this will be the same for its tail, and the height will be 1 meter here and 1 meter here, so it will be a 2 meter height in the box, for the box. So from the tip, let's choose a line, let's choose a place to create the line, and say 2 meters, T1. Okay. And from the tail, let's choose this one over here, create your line, and then say 2 meters. Okay. And this will be 1 meter, and this will be 1 meter. 1 meter over here. Okay. And then the final thing is to create the rectangle. And just choose this one over here and extend it to the bottom point. And in order to extrude, we have to delete these lines, the lines we have created, otherwise it won't extrude. And once you delete those lines, hit OK. This sketch will be your overset region. Rename it. Also extrude this 10 centimeters once again. We don't touch anything else except for body interaction. Say none. Okay. Hit OK. Apply it. Now you can see that you have created your overset box rectangle. Alright. So the important step here is to subtract the airfoil from this overset region. And we can do that by going to body groups over here, body 1 and body 2. And let's rename these. The airfoil should be airfoil, airfoil. And this should be your overset. Okay. So that's your overset. And then this is overset. Rename this. Oh, sorry. Okay. And we'll do a Boolean subtraction. So you first have to select overset region, your overset part, and then your airfoil. Right click them by holding Ctrl, select them both. Say Boolean, and then say subtract. So your tool body should be airfoil, since we're subtracting airfoil from the overset region. So your target region is your overset part. And in some cases, maybe you would like to keep the tool bodies, which will be the airfoil. We don't need the tool. We don't need airfoil, and so it automatically deletes airfoil part from your parts list. So that's what it does. If you want to keep it, it keeps it. Hit OK. So now pretty much our overset region is done. Now our overset region is pretty much done. But we have to rename the boundaries in order to actually set boundary conditions. So these two, the front surface and the back surface, will be your symmetry planes. Okay, and these will be representing oh no, could not select them. While holding Ctrl, select all these. And these will be the actual overset boundaries, overset. Okay. Now if you go here, named faces, you'll see that only the part, only this, the airfoil surface is not renamed. We can rename it, right click it, and say airfoil. And that should do it for the overset region. Check them again. Okay, symmetry planes, everything's fine. So the final step would be to create the actual domain, the background region. And we can do that by, again, creating a new sketch on XY plane. Hit create sketch. And from here, again, from the origin, let's go for 40 meters. No, 20 meters, sorry, 20 meters. Or you can, I mean, if you can go bigger, but there's no point. And from the origin, alright, so this should be 21 meters. Yeah. Alright. And then we can go up for 6 meters. By the way, you can always adjust the grid lines here. You can see them here. You can make them bigger. You can make them 5 centimeters. Or you can type it like this. And then the grid division, the division of one square, you can make it 5, 10, whatever you would like. 5 is enough. Okay, so we went up by, let's go up by 8 meters. And then same goes for this. Go up for 8 meters again. So it's 16. So it's around 40 by 16 meter rectangle. Okay, let's create our rectangle now. Delete this, delete that. Okay. So I have deleted all the extra lines. Okay, the same way we extruded the previous parts, we will extrude this one as well. Let's rename this as the air or background region. Okay. Hit right click and say extrude. Do not merge them. 0.1 meter. And there's no subtraction here, so we're pretty much done with our domain. But what's important is that we have to adjust the mesh volumetrically according to the parts. And we don't want to define a very fine mesh for every part of the region, because that would take hours to solve. And we don't want that, so we make the mesh finer regionally. So for those, we need parts. But first, let's rename this part as background. Okay. Hit save again. Never forget to save. And so we need the overset mesh and background mesh to be similar in the same region. So what we have to do is that let's first define the mesh around the airfoil. Okay. So right click this and hit show only. Alright. Restore the view. So the mesh around the airfoil should be very fine, because this is where the flow will happen. And it should be fine at its nose, or this region, its trailing edge. So the nose is the leading edge, and the trailing edge behind its trailing edge, and the whole airfoil. So we will have 3 parts for the trailing edge, the leading edge, and the whole part. Let's start with trailing edge mesh control. So what we have to do is that in the XY plane, we have to create a sketch regarding the trailing edge mesh control. So from around here, let's say 10 centimeters, okay. And from here, again 10 centimeters, and extend this up to about 1 meter. Okay. This as well. 1 meter. I don't want these lines. I just want one straight line like that. And then one straight line here. Okay. Now, let's rename the sketch. And this will be the trailing edge control. Okay. Extrude it. Everything else stays the same. Don't merge it. And hit OK. And we can actually now make the scene transparent to see what's going on. And then the next step, let's create the leading edge control. Again, let's create another sketch in XY. Let's extend this to about 20 centimeters and 15 centimeters vertically. And the length of this should be about, well, okay, yeah, this should be fine. But the length should be about 30 centimeters. Let's go down. What was the length? 15. This is 15 as well. Create your box. Delete these lines. Can actually make this line a construction line, but oh, that doesn't matter right now. It's fine. Hit OK. Rename your sketch to leading edge control. Okay, and extrude it. Don't merge it. Everything else again stays the same. Now, okay, if we imagine now the regions where these parts are covering will be volumetrically adjusted, except for the top of this airfoil, or the bottom. So we will make a part which encapsulates the whole airfoil, the surrounding airfoil. And before doing that, let's save our simulation and rename these parts by copying and pasting. So you can rename this, copy it, and then paste it. Edge control, okay. And then deleting edge control, copy that, and then paste that. Save it again. Now again, create a sketch on XY plane. Create a line that will protrude about 30 centimeters and then 30 centimeters vertically, and then here at the tip, like around the tip, let's go for 30 centimeters. I think this no, it's fine. Go up, well, not 30, but let's make the point hit the grid lines, and it will make it easier for us. And go up. All right. So the length 30, go down 30 centimeters as well. And go up like this. Okay. Delete these unnecessary lines and just put a line like this. Hit OK. Now let's rename this as airfoil control. Okay. This is the airfoil control, and extrude it. Don't merge it. Everything else again stays the same. Alright, so this is our volumetric controls for the overset region. And let's rename this to, I want to copy and paste airfoil control. Okay. Now the overset mesh and the surrounding background mesh in this region should be about similar. So we need an overlapping part in order to adjust the mesh where the overset region and the background region are overlapping. So again, let's make the background region visible. Say show, and use our background region. And we can make a sketch which encapsulates these meshes around these parts. So okay, again, XY, create the sketch. Let's make the overlapping region at about 3.5. So this is 1 meter, this should be 4.5. Should be 4.5 meters. And this should go up to 2 meters. 2 meters. Oh, we can do it more than 2 meters. Let's do it 3 meters. And then 3 meters here. Okay. Go down. Let's go down here for 3 meters. Alright. Do this. And then 3 meters here. And just connect them both. Now we can just delete these lines and connect these in one single line. Alright. Hit OK. Also extrude this as well. Extrude. Do not merge it. So okay, this will be our overlapping region. Let's rename it overlap control. Okay. Body rename. This is overlap. Okay. You don't have to. Let me check the namespaces. Overlap. Wait, overset. Airfoil. Everything is here. Okay. Cool. Save your simulation. Now everything should be set. remember we renamed our boundaries. So if we transfer these parts to files, the boundaries will automatically get created. So that's what they're good for. So try to rename your boundaries here, but you can also rename them later on in the simulation part. Here, save it again, close this part, and then we will start the actual simulation part right now. We have to transfer these parts to the simulation part of the program, and we can do that by opening Geometry tab, the 3D CAD models, and right-clicking this, saying New Geometry Part, and then say it can stay medium, it can stay fine. This is you can think of tessellation as the initial mesh of the geometry, but it's very, very coarse, so not necessarily mesh, but it's there. Okay, so remember I said that you can actually rename your boundaries in this part of the process too. So, but first we have to create a scene. So in order to rename the boundaries, we have to create a geometry scene. And here's our geometry right here. And we did not rename the boundaries, necessary boundaries for the background region. So in order to do that, you get to background in parts tab, and then you get to surfaces, you get to default, and you say split by patch. And you have to rename this surface and as well as the back surface of this as symmetry. Symmetry. Great. And then the remaining surfaces will be outside or free stream boundary condition. We don't have to we don't have to choose them there because we'll display it as default. So we can rename it as outside. And this is symmetry. Okay. So the next step would be defining regions. Regions, by regions I mean where the physics will occur. So the physics will only occur in background and overset regions, and the other parts will be only for meshing operations, which we will see later on in the video. So select background, select overset by holding Ctrl, right click them and say assign parts to regions right here. Now we don't want one region for all parts, we want separate parts for each part. So we say create a region for each part. And for this option, we would like to create a boundary for each part surface. And then anything else can stay the same. Hit apply. Now if we go down to regions, which should be open now, you'll see background and overset regions. Okay? And then background region, you can see the boundaries highlighted in purple. Well, now it's time to restore our view. We can also store the current view right now. Outside will be pre-stream. And then the symmetry will be the symmetry plane. For overset, the airfoil will stay wall. And then the overset will be overset mesh. This is very important. If you don't assign a boundary its overset condition, the mesh will not happen because the mesh for overset boundary is special. It's different from other mesh types. So you have to first assign your boundaries and then mesh, and then create your mesh operations. And this will be symmetry. Alright. The next step would be to save your simulation and then create your mesh operations. Let's create the mesh for background region. We would like to select surface remeasure. What it does is that it remeshes. Remember I talked about tessellation and tessellation is pretty much a very coarse mesh. This option remeshes your surface of the parts. And then the core volume measure will be trimmed, and then at the boundary layers there will be a prism layer measure. Hit OK, and then let's rename this as background mesh or background, your choice. You can change this execution mode to parallel to make it faster, but for our case it doesn't really matter since we will not deal with very small meshes. But if you would like more power, parallel is fine. Well, let's go with serial. And so open this tab, open default controls, and this should be the base size of 0.5 meters. And by base size, I mean every option you see here, well, some of the options you see here will be based on this size. So they work with percentage basis. You'll see now for the minimum surface size. So if you make it 100%, it will be 50 centimeters, 0.5 meters. So remember our base size is 0.5 meters. It will be according to the base size. But you can break this relation by saying absolute over here. And you can actually give your own values here. Well, let's work with relative to base option, and this will be 25. And minimum surface size is, so wherever the base size is too big for the measure, minimum surface size will get in control. So that's how it works. So you're kind of giving it a range here. And also in the volumetric growth rate right here, this should be slow. So this means that the growth rate between volumetric controls will be slow. And for the surface growth rate, this will be your growth rate from the surface of your part to the core mesh, to the core volumetric mesh. So this transition should be slow for a finer mesh. And let's create the next step. Yeah, the next step is to create the volumetric control. For parts, you have to choose overlap. So okay, for controls, set surface remeasure. Yeah, we would like to control surface remeasure, and then the isotropic size, meaning that isotropic means that the size will be the same for x, y, and z directions, but for anisotropic size, you can actually adjust the sizes in terms of x direction, y direction, and z direction. But we would like to adjust isotropic size to 12.5 meters. Yeah, percentage. So relative to the base, meaning that it's relative to this base size. Alright, hit save. We're done with background mesh. Now it's time to create our overset mesh. You can copy and paste this, or you can just drag it here. And let's do it by copying and pasting. And this will be your overset mesh. And the first thing you should do is to change input parts from background region to overset region. Alright. And then the default controls are about the same, except the prism layers will be 15. The number of prism layers will be 15, and prism layers are the layers adjacent to the airfoil surface. And these prism layers are very important to resolve boundary layers. That's why we'll have 15 prism layers here. And we would like to control the first prism layer thickness near the airfoil part surface. And we can do that by changing the distribution mode. So I'm under measures, under prism layer measure, and under distribution mode, choose wall thickness. So normally what this does is that under stretch factor, it automatically gives a thickness for the first layer of the prism layer, and then it just stretches the prism layer according to the coefficient you give. But we would like to define the first prism layer thickness. So we choose wall thickness, and this wall thickness will be 1 to the power of exponential minus 4 meters. Okay. Save it. Now the custom controls, we should rename this as overlap, and we would like to 12 point. Okay, overlap, it doesn't change. So we would like to copy and paste this again and rename this to Airfoil. And for its part, we will choose Airfoil control. Okay. The value for this will be 5. Copy and paste this again. Copy of Airfoil. This will be leading edge. Change the part to leading edge control. So you can actually, okay, overlap is there. Okay. And leading edge value will be 1. So it's 5 millimeters mesh size in this region. And finally, we would like to control the trailing edge. So this will be the trailing edge. And the part, change the part to trailing edge control. So we have 4 parts. Okay. And the value for this will be 2. So 1 centimeter around, give or take. Okay. Save it. Now we can generate the mesh. We're ready to generate the mesh. There are 2 ways to generate the mesh. You can either execute the mesh one by one by selecting them and right clicking, or execute them all, or there's a shortcut for it for executing them all, which is this button right here. So hit that button, and then let's wait for a while for it to create the mesh. My mesh is done. This might take a while. So okay. So in order to see the mesh, we can create a scene either from here, this image symbol right here, hit mesh, or you can create a mesh scene over here by right clicking the scenes and say mesh, and you can see the mesh. And it's very fine around the as you can see around the airfoil. Now the next step would be to couple these 2 regions by creating an interface, so the background region and the overset region. And right now, if you actually run the simulation, it would make no sense because there's no possible way for these 2 regions to exchange information. So we must create an interface between them, and in order to create that, we have to select the 2 regions under regions tab. Select them both by holding Ctrl, right click and say interface or set mesh interface. And now you can see the interface over here. Change this interpolation option to distance weight. Okay. Save your simulation, and then and then let's see how the mesh becomes once we initialize the interface. So hit save, and then in the interfaces, right click, say initialize, and it instantly initializes. And you can see that the overset region cut a hole in the background region. You can see it like that, okay? Now again, let's reset it to see the difference better clearly. Reset. See, the mesh here is cut. Initialize it once again. And you can see the difference. So now we are ready to actually convert this to 2D. Alright? And then we can do that by going up to the mesh tab over here, say convert to 2D, and then these should be both selected, delete 3D regions. And why we're deleting 3D regions, you may ask? Because this creates a confusion between the 2D regions and 3D regions, and it is generally better to delete 3D regions after you create your 2D mesh. So hit OK, and then your 2D mesh should be created. And do not execute these mesh operations, just leave them be. It wants to create the 3D mesh again, so don't do that. And by converting this the 3D region to 2D region, your solution will be way faster. Again, we can initialize our interface, which will be in 2D. Okay, so in order to see the cell types better, so remember hole cutting algorithm used 3 different cell types. You can actually create a scalar scene. So either from here or from the scenes by right-clicking, say scalar. We name this as overset cell status, and then for under it there will be a scalar displayer. It's called displayer, and for the scalar field we will choose overset cell status, and the range, so we're still in scalar field, and the range will be from minimum of -2 to 1. Now you won't actually see the cell types right now, so what you have to do, so in the scene you have to right click here, say apply representation, and then say overset mesh. So now you can see the active cells, the inactive cells in red, and then the blues are acceptor cells, and the green ones are the active cells. You can see them part by part. You select all. Let's see the overset region. You can see the active cells, and then the acceptor cells, and then the active cells. And in the background region, you can see the acceptor cells once again, and the inactive cell over here. So you can see the difference. So wherever there's an inactive cell in the background region, there's a corresponding active cell in the overset region. So yeah. So now the next step would be to rotate this or airfoil. And we can do that, so by rotating we're changing the angle of attack of the flow. And we can do that by coming back to regions, right clicking overset, and saying rotate. And we will rotate this to minus 2.54 degrees. You don't have to specify a vector since it is already in 2D. Hit apply, and now you can see that it has some angle to it. We can initialize our interface. Now we need some physics, obviously, in our regions, and we have to set up physics in 2D one, not the physics one. So what you have to do is right click, select models, and the models will be steady, gas. This will be a coupled flow. Coupled flow meaning there are few equations which are solved simultaneously. This will be an ideal gas, not constant density, since we're dealing with transonic flow, meaning that the Mach number, which is the ratio between your speed and the speed of sound, will be, so the Mach number will be close to 1. meaning that we're close to supersonic speeds. So, which means that the air will start to compress a lot. So we cannot choose constant density since the density of the air changes. So we need to choose ideal gas. It will be turbulent, and we'll choose Spallard-Almaer's turbulence. It's a model, and that is it. Save this. It will automatically, the region is automatic, the continua is automatically assigned to the regions. And we have to set some, but before that, let's rename this to air, physics, or anything you would like. And under it, we have to change the material properties of air, such as the dynamic viscosity to, let's delete this to 4.58 to the power of -5 pascals. Okay. And then the thermal conductivity will be 0.0638414 watt per meters Kelvin. Okay. Save it. And then you have to set some initial conditions. So for velocity in the x direction, this will be 252 meters per second. So what, in terms of Mach number, this will be 252 divided by approximately, the speed of sound is approximately 340 meters per second. Well, it will be 0.74 Mach. So we're very close to supersonic speed. So we have set our initial value for velocity, and for static temperature it will be 300 Kelvin. Okay, there's no change there. So after initial conditions, save our simulation, go back to regions, and we have to set some boundary conditions in the background region. And for the outside option, for the Mach number, we will say 0.725. And then the static temperature will be 300 Kelvin. Okay. Save it. Okay, so we're pretty much done with the simulation. We have set our initial conditions, our boundary conditions, our mesh initially, our overset mesh, and all that. Now we have to somehow see our solutions, right? Without seeing solutions, there is no point of doing the simulation. So let's create another scene, scatter scene, and rename this to Mach number scene, or anything you would like. Oops, okay. And then let's set the scalar field to, so I'm under scalar 1, to Mach number, open it, lab reference frame. Now if you initialize this, so remember we set a initial condition for our regions, for our domain, which is 252 meters per second airflow. So initialize it, and then the Mach number will be according to that. Alright, and then what you can do is that instead of for the contour style, we can make it smooth field. And alright, so this is it for the scene. So there's one thing we can do. We can actually create videos from these scenes. And we can do that by, let's create a new file in our desktop and name it as Airfoil Mach number. Okay, so this is where we will save our images. And under the scene, there will be a tab called Attributes. Open that, and there will be an Update tab. So we need to check this Save to File, and then we have to set an output directory to it, which we have named to Airfoil Mach number. Okay? And the trigger will be iterations, the image. Iteration frequency, let's make it as 25. If the program saves the image for each iteration, it will slow you down a lot. So don't do that. This will, by saying 25 to iteration frequency, it will save the image in an interval of 25 iterations. And then in hard copy, you can actually change the resolution of your images. So the output width, let's make it 720p, which corresponds to 1280 in width and 720 in height. We can use anti-aliasing, it's your choice, transparent background, and all that. And by changing this resolution, there will be a problem. And the problem would be that the fonts here will be very small, and people will not be able to read read the information you display on your image. So you can actually change the sizes of these fonts by coming to title height under color bar. The title height we can say it as 0.05, and this can be 4. So now your font size is way better. And whatever have in your scene, the image, the program will export it. Like the view you have here, it will automatically export it to that file. So we have to zoom in to our airfoil. Otherwise, we won't be able to really see the details. So zoom in a bit, adjust your scene, and then it will save it as it is. So again, save your simulation. And this star means that it is being recorded. Alright. So the scenes are done. Now we have to monitor our convergence. And we will do that by monitoring our lift and drag coefficients. Alright, so go to reports. Let's make this a little bit smaller. Say new report. And then under flow and energy, there will be force coefficients. And what we have to change here is that we have to change the reference density 1.177, and then the reference velocity 252, my bad. And for parts, we will only choose airfoil, the airfoil boundary, because we don't want to monitor anything else, only the airfoil wall, which is the wall over here. Okay. So this will be the drag coefficient, and the direction will be in x direction, because as you know, drag is in the direction of the flow. And let's create a monitor and plot from this report. Right click it and create monitor and plot. Now the second coefficient, the second thing that we will monitor will be our lift coefficient. So delete drag and say lift. And lift is in the y direction or upward direction. So we will change this to 1 and this to 0. So what these represent is the x direction, y direction, and z direction. And the part will stay the same. We have to change the direction and create another monitor and plot from this report. Hit save. And we are ready to run our simulation. One more thing. Let's create another scene, but this time it will be a vectorial scene. The vector scene, you can see that there are arrows. Well, there are two points right now, but we can change that. And geometric spacing to 5. So you can see the arrows over here. See the arrows? But a better way to display the flow behavior would be changing it display mode to line integral convolution. So it's way cleaner than the arrows that we have just seen. And you can play with this. Let's make the number of steps to 75. It makes the line smoother. The blending factor is meaning that the blending factor between the colored contour and the vectorial lines. So let's see. If we make this one, you will only see the lines. But if you decrease it, you can actually see the colorful contours. Let's make this around 6. And step size, let's make it to 1.5. And this will create a smoother image. Okay. Hit save. Alright, so we are ready to run our simulation. You can run this simulation. Well, let's set up some stopping criteria. 600 iterations is fine. 500 is even fine. Hit save again, and then run your simulation from here. And this will take a while. Okay, so my simulation is finished, and you can see the results in Mach number scene or in the vector scene. And you can see the convergence of the solution. So about 250 iterations were fine, but just in case, iterating a bit more is better. So if you come back to the Mach number scene, you can see that the flow gets supersonic on top of the winglet. And remember that as an inlet condition, we set the flow to be around 0.72 Mach. So it's not supersonic. But here you can see that the flow gets supersonic, and this creates a shock wave on top of the wing, which is not necessarily desired in the aviation community, because this causes instabilities in the flight, and hence the instabilities causes malfunctions of a lot of things in the structure of the aircraft. It's very dangerous, actually. And behind it, in the trailing edge, you can see some separation, a very low separation going on here, but it's not very drastic. It can be considered smooth. Okay. So all right, this is transonic flow in action. So you have your airfoil, your velocity is under supersonic range, which is 252 meters per second, but over your winglet, the velocity increases and becomes supersonic and creates instabilities in your flight. So this was a very huge problem during World War II, and so the experts were trying to overcome this issue. And around 1950s or so, well, before that, or after like World War II, the experts came up with solutions by changing the geometries of the airfoils. So they're called supersonic airfoils. So okay, there's one more case that we have to study, and that will be changing the angle of attack of the airfoil to about 10 degrees. So let's save this as a different copy. Let's say this as airfoil tutorial case 2. Anywhere you would like. Save it. and then transform this to rotate. Okay, so the rotation will be about minus 10 degrees. Oh, okay, minus 10 degrees. Apply. So it has changed. Since it has changed, we have to clear the solution. Oh, also, I forgot to mention, remember that we saved few pictures over here. So you can see the pictures here. You can create videos from these pictures, or you can just go back and forth. I have zoomed a bit. So we could take more frequent pictures, but so you get the idea. Alright. Alright, let's initialize the flow for this case. Zoom in a bit more to see more details, and then we can delete the pictures we have captured. We don't need them. And let's increase the iteration frequency to, let's say, 10. Okay. Hit save. We have to increase the stopping criteria for this. Let's make it 650, because you'll see that this will be more unstable. Save and then hit run. Okay, so you can actually stop your simulation since it has already converged, somewhat converged. So you don't need to go further. You don't need 650 iterations. Let's just leave it at like this. Save your simulation, and let's look at the results. Okay. So you can see that there's a huge flow separation occurring here. And again, this is not desired since this drastically decreased the lift of the airfoil and causes stall in the aircraft. So it is not desired. Here, this is where the region gets supersonic. Let's open our Mach scene. Here it is at 1.44 Mach. So here, like, you can see how there's a boundary layer separation occurring here, and this is the vortices created by the flow. Now we can go back to our saved pictures. It was in my desktop, and then let's see what happens in the flow. So it starts with a flow that is supersonic around its middle. Then as the flow progresses, it creates a boundary layer separation. And becomes steady after that. So yeah, you can make a video by selecting all of them, hitting right click and say create a video. And this is somewhat primitive, but it gets the job done. Again, here, select, say OK, select one, CTRL A, which selects all of them, and drag them here. And once you drag them here, you can again select them all. Sometimes it takes a second. Okay, and then you can change the duration of each scene. Let's make it 0.04 seconds. Oh, that's a little bit fast. Let's make it 0.1. Let's see what happens. You can see how the flow progresses. And after this, you can finish your video, publish it, and all that. So if you want to make a smoother video, you can decrease the iteration frequencies where the program captures the images, but again, that's computationally expensive. It slows down your solutions. So it's your choice. So let's look at the you can play with the vector scene for a better. Let's see, vector line integrals convolution. If you make the blending factor 1, you can see the vortices better. See how beautiful they are. So yeah, this is a tutorial. Hopefully it helped you. You can play with the simulation. I mean, there are a lot of things to play with. You can rotate your background, your overset region, your airfoil. You can change the, I don't know, the speed of the inlets, the speed of the velocity of the flow, and all that. So hopefully this video will help you, and have a nice day.